Hello, hello, hello. Testing, testing, testing. Hello, hello. Testing, testing, testing. Hello, hello. Cool. Okay. Testing, testing, testing. Right, yes. So, uh, first things first, got to do my Duolingo, to do my Greek lesson. Um, and then I'll discuss what I'm gonna do. So, let me just drag over the Duolingo screen. Yeah, okay. I haven't done this for a while, I'm a bit lost. Okay, cool. Right, so Greek, let's go to that. Yikes, it's been a while. Maybe we should just remind ourselves of how this works. Ze,
An,
an,
ze,
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 ze, vi,
v.
ve, vi,
I, okay, v. Cool. Ria,
ria, na,
na. This v is the n, and the p was the r before. Good that I remember that. So this is going to be na.
na,
Na.
ma,
Ma. This little funny thing is a ma. M, sorry.
Mark και Maria.
Mark and Maria. So
Mark,
R,
Maria,
R.
Mark και
Nothing else interesting there. Yep. Ma, which is this funny thing.
ma, Maria το καρότο.
Maria the carrot. Nice. I don't know how to spell carrot. Is it double T? Who knows?
Ria,
Ria. People will know.
ria, vi,
V.
vi, το mini market.
The mini market. That's M and N
Market,
and the R just there.
να,
Na.
να, να.
Yeah.
Ναι, Maria.
Ne is oh no, I know this one. What is ne? Ne. Ne Maria. It's not there. Maybe it is there. No, that's to. But maybe ne. Oh god, I can't remember.
Ναι,
Yes, alright. Wouldn't have got that one. Glad we're doing this again.
ναι.
Fair enough. Anne.
Mark το mini market.
Mark the mini market.
Ναι, το mini market.
Yes, the mini market. Alright. Let's do the other one, and then we'll move on to what I want to do. Ooh, not quite yet.
Πώς. 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 Με.
Me.
Με. Snow.
Snore. This is sigma, I think, so that's why it's an S. Snore.
Snow.
Snore.
Με.
Me.
Snow.
Snore.
Snow. Ναι, το βίντεο.
Ne.
Ναι,
To.
το βίντεο.
Video. Yeah, I always forget this one. But this is apparently a V. I think so, because I was guessing it was beta. Veteo. It might be silent B, something like that. I don't know. Let's just listen to it again.
Ναι, το βίντεο.
Because it's also got the N as well. It's very strange. Video. It's like N is completely silenced. Anyway. Seo. Sigma
Seo.
again. Seo.
Σίο.
Seo.
Σίο.
Ste.
Στε. Αυτός κάνει βίντεο.
Aftos is he, I think. Kane is he something the video. I remember struggling with this last time.
Κάνει.
Makes. He makes a video. Okay. Video. Video.
Βίντεο.
I wish it would explain
Στε.
why. Stare. Oh,
Στε.
select the correct characters for me. Me.
Με. Σνακ με ούζο.
Snack. This is sigma again,
Snack.
but capital. Snack. With ouzo is a liquor, I think, but I can't remember how to spell it.
Ούζο.
Ouzo. Okay.
Ούζο με σνακ.
Ouzo with snack.
Σινεμά και μουσείο.
Cinema and M. Yeah, museum.
Το σνακ στο σινεμά.
The snack. Sto is, I don't know.
Στο.
At the snack at the cinema. At the. I've
Βίντεο
forgotten
και
one of those
σνακ.
already. Video and snack.
Το σινεμά στο μουσείο.
The cinema at the museum.
Το σνακ με ούζο.
The snack with ouzo. Cool. Okay, so what I wanted to do today, and I severely need to go back through that again, is right. Yes. God. Now I have to remind myself what that was. Yes. I want to look at the Schrodinger equation properly now, like to start to understand how it affects the position of electrons, or how to use it to figure them out, basically. So there's lots to study there, and I'm also very aware of the Heisenberg uncertainty principle, which is some kind of notation to denote that when you know angular momentum more precisely, you know position less precisely, and vice versa. So we know those things. I think I've discussed them before, but I want to look into them now. I don't have too much time because I'm just so tired, but at the same time, I couldn't wait another day. I've just wanted to do this for so long. So we're going to move away from code for now. Just going to get a nice base understanding of, or just even to have a little peek at those equations. And the reason is because I would like to aim for, this is episode 23. What does it say last time actually? This is 22, so we're laying out electron configurations. We finished our electron configuration numbering and are ready to continue on this learning material. Okay, good. Good for me. So yeah, the reason I want to do it is I want to have in Unreal Engine the ability to have an atom with a certain electron configuration, and that's important because that will denote elements in the periodic table. So let's imagine this atom has, or this particle has, a couple of electrons, and I want to start to know what the position is of electrons. If that's a probability, then that's fine. If I know that it's roughly around here, or if it's roughly around here, that's what I want to know. And in Unreal Engine, that would end up being a kind of a 3D model with a kind of yeah, an area that is filled with a color that denotes position. That will be all well and good. I know it's going to be difficult because I don't know how. Don't know how to form a kind of surrounding geometry around lots of points. So there's a little bit of learning there because I'm going to have a big long array of different points. I need to find the maximum of those points and then form some kind of automatic geometric shape around them, area around them. So that's the goal. Finally speaking, I would like to do this in Mathematica as well, or yeah, so Stephen Wolfram's Mathematica. One sec, just gonna close the door. And that's because I want to start to learn some of the tooling that science uses, basically. Cool. Let me just keep that drawing in actually, and I'll make it small. So beer of the day is non-alcoholic, I think, 0.4%. Just trying to keep my brain a bit sharper recently. That will change tomorrow. I'm going to go to the pub. Oh, and I had a beer today. Oh well, it's alright. It's quite fruity. Anyway, let's do this then. So, diving begins. Um, so let's start with Schrodinger equation. And I know the first question that's going to come up is what the heck is a wave function? Like, what does it mean to represent? What does it mean in terms of data? Um, so let's start with the wiki article, I guess. I have donated to this. I suggest you do too. Can you imagine without wiki? Oh, I couldn't imagine it. It'd be horrible. Um, I only donated like £5 though. I think. I think that was right. Yeah. Um, hopefully it helps. Okay, so there's the equation, this beautiful thing, absolutely beautiful thing. Let me just copy this, paste it into here somewhere. Oops, it did not work. That's not working. I'm a bit fed up of OneDrive. It's not. Sorry, OneNote. It's not that good. Like, why does it keep disappearing? Oh my god, I just want to get on with this. Let's take a screenshot of it or something. Maybe that will help better. There you go. Cool. So the way I understand it is this hit a bit thicker please. I want that thickness. Yeah. So this stands for imaginary number. Uh, imaginary making all outputs of this a complex number. I think that's what that means. Now this is the Planck constant, I think. So Planck, can't remember how to spell his name, something like that. It's Planck constant. Yeah, C and a K, good, that'll do. Planck constant, which is, the way I remember it is that it is the amount of energy to emit an electron from a configuration. I think that's right. This is to denote some special differential equation. It is maybe partial differential equation. Let me just check that. Uh, partial differential notation, Leibniz. I think it's that. Um, God, maybe not. What does curly D represent in differential? Um, different forms of D for differential equation. I just can't remember what it means. Classical classification. Notation difference for partial differential equation. Come on. Yes, okay. I can see some of those things now. Um, what letter is that as well? That is still delta, right? It has to be. It has to be delta, yeah. Um, partial. And partial differential is an equation which imposes relations between the various partial derivatives. Yeah, we know that. Need to be solved for similarity to how x is thought of as an unknown number to be solved for. Um, I'm trying to find. Yeah, because if I just do partial, is it s- an one order differential equation or something like that? First order. Okay, yeah. So first order differential notation versus second order. I'll explain this in a second. I've just gotta remember what the symbol is. So this has got differential equations. Um, Newton lists the three kinds of differential equations. Okay, here we go. So dy over dx equals a function of x. In all these cases, y is an unknown function of x, or of x1 and x2. And f is a given function. He solves these examples and others using infinite series and discusses the non-uniqueness of solutions. Bernoulli proposed the Bernoulli differential equation in 1695. This is an ordinary differential equation of the form y, first derivative of y plus, looks like a probability thing, p of x of y is equal to, I can't remember this, uh, the first derivative plus a function of x times y is equal to, okay, so let's read on. For which the following year Leibniz obtained solutions by simplifying it. Historically, the problem of a vibrating string such as that of a musical instrument was studied by Jean Léron d'Alembert, Jean Léron d'Alembert, Leonard Euler, Daniel Bernoulli, Bernoulli, I don't know, and Joseph Lagrange. Oh yeah, Lagrange. We know that Lagrange. In 1746, discovered the one-dimensional wave equation, and within 10 years, Euler discovered the three-dimensional wave equation. Blah blah blah. Where are we finding this D? Okay. Heterogeneous first-order linear heterogeneous first-order linear constant coefficient ordinary differential equation. So let me just remind myself what that means. Diverse in character or content. So it's a diverse first order linear constant. So it's just going to go one line coefficient. So that's the coefficient is the variable in there. Ordinary. I don't know what ordinary means. Differential equation. Okay. And the second order is the okay. So the first and second order just denotes if it's a second or first derivative, which is the slope of the curve. Yeah, it is. Cool. Good. Learned something new today. The homogeneous second order linear constant coefficient ordinary differential equation describing the harmonic oscillator. This is this uh, angular moment. This stands for angular momentum. I swear it does. Let me go to my question because I've actually, bear with me. Got a little, oh, I'll have to do it over here. Got a little question I asked on Stack Overflow once, and I know that I covered this. Physics, where are you? Physics, physics, physics. There. And then my questions here. Yes, okay. So, stepping function, what did I do? Ah, angular velocity. Fuck. That's so annoying. I did know that. Ah, what a shame. Okay, fair enough. Um, Angular velocity. Yeah, okay. Let me just go back to that then. So in terms of a harmonic oscillator, it's the angular velocity squared times by u, which represents what? God knows. I guess anything, but I think. Oh, here we go. Let's just have a look. The u. What does the u stand for? Um, where are you? U. Okay, fine. So this instead will be w squared. So where's the squared in this? Initial condition. That's not it. Here we go. No, squared x. Okay, maybe it just stands for anything then. Doesn't really say, does it? Okay, so good. Heterogeneous first order non-linear ordinary differential equation. So yeah, it's the first derivative. Yep, it's non-linear because it's squared. So this is linear. Oh, non-linear. Linear differential equation. Ah, no, I can't even remember what the difference is between those two now. Ah, that's so annoying. Difference between linear and non-linear equation. So I think one draws a constant line, the other bends, right? Pretty sure that's right. See a nice diagram here. Here we go. Yeah, okay. Fine, so that is exactly what that means. So this one is linear, which is interesting because it still has that to the power of 2. But oh no, because it's plus, I see. It's equal to 0. This one, however, is equal to an exponential plus 4, which just offsets it, I think. I guess so. Then you've got this second differential non-linear, okay, because it's got sine in it. Due to sine function, there you go. Ordinary differential equation. Ordinary differential equation. So what's this ordinary part? I need to know this stuff because I need to know that formula. So uh, what does ordinary mean in an equation? Yeah. An ordinary differential equation is an equation that involves some ordinary derivatives, as opposed to partial derivatives of a function. Okay, so I think partial is when you partial derivative. Ordinary versus partial. Sugar. I can't remember this stuff. Um, what is a partial? Difference between ordinary and partial differential equation. Okay. The order of a differential equation is the highest order of any differential contained in it. For example, oh, you can't see this stuff, sorry. There we go. Examples. Here's your dy over dx is equal to a times x is first order. D3 is third order. And this partial is second order, and this is just simply because of this red, because this denotes how many times you take the slope of the graph. Yes. Ordinary versus partial. An ordinary differential equation contains differentials with respect to only one variable. Partial contain differentials with respect to several independent variables. So this is the okay, so examples dy over dx are ordinary, but this is z over x and y. So the change in x and y, okay, and the equality between x and y are partial differentials. The straight and curly d's give it away if used properly. The real, oh, there we go. Okay, we got it. Finally, the answer. So when we go back to our thing, this notation means that it's a partial differential equation. That means that there are several variables that are acting upon it. Now that's interesting. It just doesn't denote what they are. I guess it's kind of trying to be generic about things. Bit of a guess, but anyway, let me put partial differential. Whoa. Okay, differential. Now, this part is the wave function. No, sorry. This is a wave function of time. So a wave function with respect to time. Good. Okay. This bracket notation denotes it's like a vector. It's like a matrix, I think. But I think it basically means a vector. But it doesn't have like x, y, and z coordinates, or z, whatever you call it. I don't think that it has that. So I need to look that up now. So let's get that up. Bracket notation. Yes, wiki, please. The bracket notation. Oh, look. Schrodinger equation, or Dirac notation, is used ubiquitously to denote quantum states. The notation uses angle brackets and a vertical bar to construct bras and kets. A ket is of the form that, mathematically it denotes a vector, okay, good, v in an abstract complex vector space. That's the difference. Complex vector space, the way I understand it is that you have yeah, it's like it has this kind of rule. So if so I is equal to -1, I believe is the rule, and as you circle round, you say what? I can't remember now. Let me have a look at this then. So, um, imaginary number graph. Okay, fine. Yes, that makes sense. So it's plus it's I plus minus. Oops. I minus, and then you got 1 to 1 to -1. Good. And let me just make sure that imaginary rule is correct. Imaginary number axiom. I'm pretty sure it is that. Uh, I squared is equal to -1. Oh, that might be it then. Since we start with an axiom, I squared is equal to -1, which does not explicitly contradict any other axiom in the real numbers, since I does not appear in other axioms. There is no way to directly disprove it, but in a slight modification to the aforementioned, there are some axioms which are actually disproven by C, like trichotomy. Great, good for you. I cubed. Yes, that's right. Yeah, it is I squared. Um, so because I have to remind myself of the rule here. So if it is I squared is equal to -1, then what's I cubed? Well, if I squared is equal to -1, then no, that can't be right. What's the axiom for imaginary number? I equals -1, something like that. Let me just put imaginary number. It is, which is defined by its property I squared equals -1. Alright, okay, so we can start to work this out. So if I squared equals -1, then what is I cubed? I cubed would be -1 times, it'd be okay, so sorry, maths is a little shaky here. So if I go, let me just do this, just straight up do it. If I were to go 2 squared, then you're going to have 4. And if you were to do 2 to the power of 3, you're going to have 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. That's not right. Oh my god, I'm so bad at maths. Shitting hell. I hate myself. Clearly hate myself. That's wrong. Okay, 2 to the power of 3. Oh, it is 8. Fucking hell. Okay, whatever. Good. Sorry about that. So, that makes sense. So then it's 2 times 2 times 2, and this is 2 times 2. So this will be, um, it'll be -1 times, oh, what's half of, no. It'll be, so I squared, I3 will be the same as I times itself 3 times. So if I squared is -1, then I must be, because well, it's kind of illogical, isn't it? Not sure now. Yeah, I don't think it's logical. Okay, let's try this again. So I3 is, what multiplied by itself twice can be -1? Let's just do that. So -1 times -1 equals 1. I guess there's nothing then, right? So that's why that is so interesting. But I3, it must be I2 times I2 times I3 is equal to, if I2 is equal to -1, Oh, you know what? It doesn't matter because it's gonna be 4 times 2. So in this case, it's minus 1 times 2. So what's minus 1 times 2? No, sorry. What's minus 1 times minus 1? Minus 1 times minus 1 is 1. Good. Okay, that makes sense. Now what's I4? I4 would be um, let me just put this in a different color actually because it's confusing me. Yeah, let's go light blue. 1 minus 1. Get rid of that. Get rid of that. So I4 is going to be um, well, 1 times 1. Sorry, that's not very clear here. I to the power of 4. That can't be 1 again, can it? Oh no, it's negative. So it's, oh god, this is difficult. Negative 1 times negative 1. So this is going to be times. It's I times I is negative 1. So we have to start from there. So there's our starting clause. Then we multiply it by I. But we don't know what I is. I squared is if that's minus 1. Oh man. I've done this before as well. This is the worst part. I can't remember how this all works. You have to be very logical. Let me just try this again. Let me just start totally again. Um, right. I to the power of 2 is equal to negative 1. That's the axiom. Okay. So if we want to do I to the power of 3, I to the power of 3 is going to be, it has to be minus 1 times minus 1. It's minus 1 times I. That's the problem. But we are told here that 2 of something makes negative 1. And and negative 1 times 1, negative 1 times, oh my goodness, what is wrong with me today? Nothing. I just don't know this stuff. Okay, okay. Whew, this is difficult for me, sorry. Um, exponent rules. Nope. If I squared is equal to negative 1, and if I do 2 squared again, I'm gonna have to write this out again. 2 squared is equal to 4, but that's because it is number based. So that is literally 2 times 2. Now this one is I squared is equal to I times I. And negative 1 can I times I. If I squared is negative 1, what was what's the what's the log of I, right? What's the log of I squared? Okay, fine. Let me get a hint then. That's fine. I squared, I cubed, um, imaginary numbers, I2, I3. Let's get that. Or is this like GCSE again or something? Um, we already know that I1 is equal to I. Ah, oh, mate. God, see that's beautiful logic. That is why I love maths. Oh my god. I mean, it's just so ridiculously, stupidly obvious. Of course, um, I is equal to I squared is equal to, or at least I1 is equal to I to the power of 2 is equal to negative 1. But now we've got, well, no, we didn't have much. No, let's carry on. I got a little excited then. Uh, so, we, so that is I1, I2, and so on up to, okay. We already know that I1 is equal to I, and I2 is equal to negative 1. So the rest are I3 is equal to I times I2. I times I2. Okay, that makes sense. So equal to I times I2. And that's going to be I times I2 is going to be I times minus 1. I times minus 1 is going to be negative I. Ha 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 ha. Okay, right. Now we're getting somewhere. Whew. Sorry, mathematicians. I am so sorry. Oh, God. I hate myself. Don't worry. You don't have to hate me. I'll hate myself. Thank you. Equals negative I. Yes, that makes sense. Okay, so I4. Let's just push this a bit more. I4 is going to be um, I I2 times uh, times. So it's okay. So if I3 is that, then it's going to be negative I times I, right? What's negative I times I? Um, Negative I times I is going to be negative I still. That can't be right. But we have a number here. So let me just think about this again. So we've definitely got this negative I now, because that's I times negative 1 equals I times negative 1 equals negative I. That makes sense. I times negative 1 is negative I. So if I3 is equal to I, no, okay, yeah, that, then this is going to be times I. Hmm. Whew, okay. I minus 1 minus I4 okay, this should be easy. Just think like a mathematician. What would they say? They'd say, look at the laws, look at the rules. What can we deduce from this? We can deduce that we just need one more I multiplied from negative I. But negative I is not a number. Now we can do I to the power of 2 times I to the power of 2 would be so it's negative 1 times negative 1 equals 1. Maybe. Let's try that. Let's see how we go. Let's see how we go. And I5, if, so it's going to be, I5 is 1 times I, so it's going to be 1 times I, because if this is 1, then it's just multiplied by I again. Sorry. Sorry. Yeah. Okay. Yeah. So 1 times 1 more I is going to be I. That makes some sense. Uh, let's try. I know because there's something that happens here. There's like a loop, and I want to re-exercise this muscle, um, because I know it's going to come up. This kind of critically logical thinking, whatever it's called. Okay, so if that's true, then what's I times I? Uh, if I5 is I times I is I squared. This is crazy. I squared. And there should be a loop here, I think. Is this one? I7 is equal to I squared times I. No, hang on though. Because I squared must equal minus 1, so this must be minus 1. Ah, you see? You see? Got him. Yes, yes, yes. I squared. Got him. And so now it's going to be minus 1 times I is equal to negative I. And we're back round in a circle. Okay, good. We got there. This carries on forever now. So let's just double check this. So we've got, let's see. So I4 is equal to 1. I3 is equal to negative I. I5 is equal to I. Yep. Oh, so they did I times I times, yeah, I did that as well. Cool. I6 is equal to -1, yep, and I7 is equal to -I, and thus I8 is equal to 1 because this is when it starts to go around, and so on and so forth. Okay, cool, good. So we understand that. And we now also know that so with that in mind, what were we doing? We were trying to look at, um, this complex graph. Uh, so if you imagine, oh, you can't see that. If you imagine that we had coordinates with i's in them, then this starts to make sense, right? Let's imagine that we have I squared, I plus, I negative. I squared would be going up here because I is getting bigger. I squared. Let me look at a plot. No, let me think about this. Where would I squared be on this graph? Or where would 2i be? It would be 2i would be, let's imagine this, it would be here, right? 2i would be there. So let's just see if that's correct. 2i on a complex plane. So 3 plus 4i. Yeah, okay, so they have done exactly that. Great. That's 2i, so good. Okay. So you see how because you now have your axis as I, you can start to navigate a graph with the imaginary plane, the complex plane. Good, that makes sense. So this wave function with relationship with respect to time, and this is all equal to um yeah, actually I don't know what h hat is. H hat. H bar is definitely Planck's constant, and h hat is hmm not sure, but interestingly enough, I think because it's multiplied by the wave function with respect to time. No, I can't remember what that means. I think I've written it down in my 1 second, give me a sec. I'm pretty sure I've written this down before. Somewhere here. Here we go. No, I haven't. I actually haven't. That's interesting. So I never wrote the actual equality of it. That's a shame. Okay. So we need to figure out what that equality means. Let's go back to our, close this probably actually, our Schrodinger equation. Yeah, here we are. Let me zoom in. Oh, that's interesting as well because they've got the coordinate here. So this is position over time. You would expect, right? A position, whatever that is. Um, this is definitely the left side of our equation. Let me just split the screen for a sec. So in the actual definition of this equation up here, you see it's not in relationship to x or respect to x. And however, okay, so oh, this is beautiful. This is that is the complex plane. That, yeah, here you go. Complex plot of a wave function. That's very nice. Okay. Um, Introductory courses on physics or chemistry typically introduce the Schrodinger equation in a way that can be appreciated knowing only the concept and notations of basic calculus, particularly derivatives with respect to space and time. A special case of the Schrodinger equation that admits a statement in those terms is the position space Schrodinger equation. That's where the extra x is coming from. For a single non-relativistic particle in one dimension. For a single non-relativistic, I wonder if this gives a nod to general relativity or if it's just a mathematical term. I don't know. Non-relativistic Schrodinger. Maybe it's not. Although you know, I still I think that Schrodinger worked very closely with the general relativity equation, so maybe it is a nod to it. Particle in one dimension. Anyway, cool. Now this equality is different. So either yeah, because this becomes the second order of Planck over 2m, where m is the mass of the particle, okay, and the partial second derivative, second partial derivative, the second partial derivative, second derivative of the partial equation, maybe it's like that, um, is with respect to a position squared plus v the potential that represents the environment in which the particle exists, the potential, scalar potential. Ooh, okay, yikes, Scoob. Let me just do a blood test for my diabetes. If you don't watch me, no one watches me, so that's all right. I lie. Some people are watching. I'm not sure who they are, but they are watching. Just not live. That's all. Might be bots actually. That could be that for some reason. Yeah, I thought it was going to be a bit high. 11.7, not that great. It's probably because that beer, it's got a bit of sugar in maybe. Not sure. Little injection should do the job. Let's go for a, yeah. Good. Okay. So I'm not sure at the moment. I don't think I want to go onto this. This is adding this position space thing. I would like to understand what this. So this might be. I think there's a special space in which you can operate. That H hat might refer to Hamiltonian something. Um, let's find out. Anyway, oh, didn't mean to do that. It probably doesn't. Heisenberg, yeah. Yep. H bar, here we go. H hat. Um, well, unless maybe hat is mentioned. What does the H hat represent in what's the of an equation called? Yeah, okay, so in the right side of the equation. In the right hand side of the equation. Hamiltonian. Hang on. There's no way I was right. That was a complete guess. No way! Oh my god. In quantum mechanics, the Hamiltonian of a system is an operator corresponding to the total energy of that system. Is an operator, keyword, corresponding to the total energy of that system. So the wave function is scaled by the energy, multiplied by, including both kinetic and potential energy. Its spectrum, the system's energy spectrum, or its set of energy eigenvalues, is the set of possible outcomes obtainable from a measurement of the system's total energy. Due to its close relation to the energy spectrum and time evolution of a system, it is of fundamental importance in most formulations of quantum theory. The Hamiltonian is named after William Rowan Hamilton, who developed a revolutionary reformulation of Newtonian mechanics, known as Hamiltonian mechanics, which was historically important to the development of quantum physics. Similar to vector notation, it is typically denoted by h hat, where the hat indicates that it is an operator. It can also be written as capital H or this thing. Oh, it's another symbol I don't know in languages. Um, Great. Okay, well that was a good guess, wasn't it? That was a good guess. Hamiltonian. Hamiltonian. I think it says space. No, it didn't. Okay, so I just had the wrong thing. So it's actually is an operator corresponding to total energy of that system. Sweet. All right, that's good. And this is just that same wave function is there. So these are equalities. That's really interesting. So it's saying that whatever the imaginary number is multiplied by the Planck's constant, multiplied by this partial differential equation, multiplied by the wave function, is equal to the total energy of the wave function, or total energy multiplied by the wave function, if I'm reading that right. What does that mean, is the question now. So what kinds of data might we put into this? Let's take a step back a second and put some kind of more numbers into things like this. So let's imagine a graph, right? How's that blue working for you? Not bad. Let's go pink. It's a bit more poppy, right? Okay. So let's imagine we have a graph, and let's imagine that h bar is 2, right? It's not, but let's imagine h bar is 2. And the imaginary number is multiplied by that, so it's going to be 2i. Let's do this kind of squiffy thing as well to really denote that that's the imaginary thing. So we've got 2i here multiplied by the differential or the partial differential for with respect to time. So okay, so let's imagine that partial differential creates a, I don't know, oh let's imagine it creates a sine wave, right? So let's imagine that, something like that. Wait, that's a bad sine wave. Sine of x is equal to -1. No, I can't remember. Let's just look at sine wave. Sorry. Sine wave. on graph. It crosses 0. Okay, good. So it's going to be something like this. Okay, so here's our graph, right? That's the differential part. So we've got 2i, 2 times I multiplied by the output of this graph. Now this is the first derivative. So we just want the slope of the graph. So let's imagine at t, so this is t, and this is, I don't know, something. I don't know, let's put a little question mark there. I don't know what this is. So at some point on t, let's say we get the gradient of 0 here. So let's say this is negative, I don't know, -2 at point P, right? Oh, let's call it A for ass. Love a good a point of ass, an ass point. There's the ass point. So it's now going to be 2I, whoops, A. Let's put a little multiplied there. Now, that's all well and good. This is the part that I don't understand. What the heck is the wave function? Now um this this letter here, I think it's Greek. Let's go and have a little look. Keyboard, please. Keyboard. Greek. Yes, it's looking like this, isn't it? XC. C. Oh, that's weird. Yeah, because I would have expected a wave to be a W. So I wonder how you pronounce that letter. How do Woo, nope. That? Nope, that. Okay. How do you pronounce that? Psi. Psi. Why would it be called psi? Why is Schrodinger's equation uh, wave function labeled with psi? By analogy with waves such as those of sound, a wave function designated by the Greek letter psi may be thought of as an expression for the amplitude of the particle wave. Psi. P. Particle wave. Or a de Broglie wave. Although for such waves, amplitude has no physical significance. Great. We know that. Um, so I wonder if it's psi because... So is psi a P? Is psi a replacement for P? Okay, Greek words with psi in them. English P. Yes, 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 yes. Particle function. That makes sense. Okay, so that's why it's psi. Good. So it's the particle function for T. Okay, that's good. That's helpful. So let's probably write that down actually. Uh, let's point to that. So this, let's close this down. This letter psi is in English P, which could stand for particle. Okie dokie. That's good stuff there. Yeah, I'm happy with that. So this is going to be then wave function. I wonder if it's just any function with respect to time. It's a wave function. So it's okay. So it's any function that expresses the location on a graph for that for the wave itself. So let's imagine, right, that the sine wave was our not only was it our output of the differential, but oh, I see. Yes. So the differential is acting upon the wave graphs. Okay, so let's really imagine that the sine wave is our particle function, right? So our in this case, psi is equal to sine, right? Let's imagine that. And now, with respect to t, we can take our derivative of sine with respect to t, and then multiply that by Planck's constant, which is also multiplied by an imaginary number. Now, I need to now understand what kind of coordinates do bracket notations look like. So let's have some examples of that, because I need to start collecting some data to visualize, right? Um, I will have to link that to electrons soon, but not yet. Let's just start really simple. God, we're getting really good at the moment. I need to go to the toilet as well. God. Okay, so um, example of coordinates for a wave equation with a particle wave function. Yeah, because whatever it outputs coordinates essentially. That's what it's saying. It's saying this function. Let me actually point to this function here, right? It returns a a bracket vector. So it returns a position. Now, I think as well there is in that function there must be some probability clause. So let's imagine a piece of code. For example, let's say we've got a function called um, uh, particle, uh, or let's call it get particle position, right? And we're going to pass in time. So this is going to be at this point in time, where is this particle? But it returns a vector. So if we're talking about okay, let's go Python here. So it'd be a definition. We'd have our our little self and our t here for time, and then we're going to be returning a vector. A vector, or yeah, a vector, and it's going to be a vector with some range of probability, I suppose, but maybe not. Maybe the function is still just returning a vector, but at the same time, it's denoting that in that function there is some probability clause. Anyway, and this is exactly what's happening. So That's not how you do this notation. Shit, how do you do that again? Maybe it's like that, vector, and then it's like that, yeah. So there's our our code version of this. That makes sense. Okay, there's our code version. Good. So yeah, once again, need to know what a wave function is denoted like. Can it be anything? I don't know. Um, Example of coordinates for a particle wave function. I don't think it's an example of coordinates. I think it is simply x, y, and z, or on the imaginary plane, or on the complex plane. I mean, that doesn't help us though. Even if it was on the imaginary or the complex plane, we don't have a position in space time, which means that we can't run classical physics against it, right? Um, with forces that get applied to each electron. So it probably is. It probably is just an x, y, and z coordinate, or at least we want it to be, right? I think that's right. Yeah, because I mean, what does this even mean if it's going to be a complex number? Yeah, I think this is probably where it gets a bit complex now. Ha! Yeah. Yes. Okay. So I think worth going back to this again. This diagram here is wonderful because you can see it's kind of got this kind of 3D feeling of it about it. Kind of it spirals out in this 3D fashion. But note that it's a complex plot. So these numbers are not actual positions in a space, right? This is just some kind of very abstract space that it's running in. So the question is why that needs to be done. Because anything that we output from this Schrodinger equation ends up being multiplied by the imaginary number, and so it becomes complex. Ah, yeah, I wish I knew this. This might be where I need to stop and do a little bit more revision myself. Okay, so let's just see a little bit more. Let's push it a little bit harder. I have learnt something today. Well, mostly revision, but I have learnt something. Here, the wave function of with position. So that's interesting because here we're passing in a position. We're saying it's not only that we have t coming in. This is saying, well, we should do another one here. This is saying that we have a request for a position at a certain time. You're saying what does this function do to my position? So are you asking for, are you saying that my electron, if my electron is there, then what are all possibilities? Is this instead returning an array of vectors? I don't know. So it says here the wave function with respect, the wave function as you pass in x and t with respect to x and t is a wave function, a function that assigns a complex number to each point x at each time t. The parameter m is the mass of the particle, and v for x and t is the potential that represents the environment in which the particle exists, the potential. and simply stated describes a situation where the difference in the potential energies of an object in two different positions depends only on the positions, not upon the path taken by the object in travelling from one position to the other. It is a scalar field in three-dimensional space, a directionless value. Oh, in three space. Wait, let's just plop into that and we can close those other ones now. Close to right, where is it? Close multiple tabs, close tabs to the right. Yeah. Scalar potential simply said not upon the path taken by the object in travelling from one position to the other. So simply stated describes a situation where the difference in the potential energies of an object in two different positions depends only on the position. Describes the situation where the difference in the potential energies of an object in two different positions. It describes that, the potential energy. But it describes a situation where the energies of those two objects depend only on the positions. The energies of those two objects are denoted by the position of the objects. Ah, I get it. That's crazy. Okay. Yes, that makes a lot of sense. Not upon the path taken by the object in travelling from one position to the other. It is the very position of them that denotes the energy rather than where they have travelled. Okay, it is a scalar field in three space, a directionless value, scalar, that depends only on its location. A familiar example is potential energy due to gravity. Yeah, okay. Why? Potential energy due to gravity. Potential energy due to gravity is potential energy due to gravity. Ah, yes, because it's not kinetic energy yet, so it's not doing any differentiation on it. It already knows its sum total of potential energy at any given point in time, at any given point, sorry, in space. So let's go on. A scalar potential is a fundamental concept in vector analysis and physics. The adjective scalar is frequently omitted if there is no danger of confusion with vector potential. The scalar potential is an example of a scalar field. Given a vector field F, the scalar potential P is defined such that F, the vector field, is equal to the negative of, now this isn't change. This is not change. So what does upside down delta mean in maths? The upside down capital delta symbol, also called Nabla, used to denote the gradient and other vector derivatives. Wait, this is the changing though. Gradient. What's the difference between then? You know what? Let's, how did we get here? Let's try and find it. Is there, cite this as, see also, um, a vector derivative. Difference between delta and upside down delta triangle. So that's the delta symbol. means change or the change in. So what's the difference between the other one? Okay, so difference between delta and nabla. Delta is a Greek letter, uppercase, delta is generally used in calculus. Delta is the fourth, The inverted Greek delta is read as del sometimes. The inverted Greek delta is nabla. Nabla is generally used in vectors for the gradient. The gradient of a vector? I didn't know that. I did not know that. Delta is difference of any quantity examined at 2 points, i.e. the delta t2 minus t1, which results scalar, while del, or nabla, gives you gradient of temperature, results vector. That's not helpful. This might be though. Nope. What is the difference between that and that? There's nothing, right? When I first started studying it, we used a lot, but in more recent times I've barely seen it. To find the gradient of a curve, but yeah, there's no difference there. Del is a mathematical function, a differential operator for vectors, usually denoted by an upside down capital D. The word is sometimes also used to refer to that symbol in other contexts. It is also called nabla or atled, the latter being delta backwards. So it's specific to vectors. The gradient of a vector. So what does a gradient of a vector look like then? Let's just imagine a graph, and we've got a vector here, and our vector is from 0 to there, right? So there's our v1, right? So the change in v1 is going to be a coordinate system. It's going to be x, y, minus x2, y, y2 is that. Whereas this would be uh, x minus x2. Well, the other, you know what I mean, the other way around. Let me just do this properly. X2 minus x. That's the change. And this should be the other way around as well. Well, that doesn't feel right. It seems so. Like, surely the other one's just enough to denote the change in a vector as well. Like, very strange. Nabla. Nabla. No. This is delta. This is nabla. Nabla. What does nabla mean? Let's figure out what now. What does nabla mean? For a Hebrew harp. Harp. Math. I don't know. I think I'm gonna go to bed now. But this has been really good. Um, I'm actually because I basically swing between doing game stuff and this. I I think I'm gonna try and force myself tomorrow to do this again. Um, depending on my mental agility tomorrow. Um, so where have we stopped? We're still trying to understand what. This is the part I don't know. Still trying to understand what kind of stuff comes out of this function or what goes in. And we've kind of thought already that um, this this is a function that takes t and outputs uh, a vector. That's it. That's basically all I've got to at the moment. Um, and we were trying to work out this here, but we need to know the difference between the notation. So that's a good place to stop. As always, I say keep learning, keep loving, and we'll catch each other on the flip side. Have a good life. See you soon.